Hi, welcome to Unsupervised Learning in Python. Unsupervised learning encompasses a variety of techniques in machine learning, from clustering to dimension reduction to matrix factorization. In this course, you'll learn the fundamentals of unsupervised learning and implement the essential algorithms using scikit-learn and scipy. You will learn how to cluster, transform, visualize, and extract insights from unlabeled datasets, and end the course by building a recommender system to recommend popular musical artists. This course consists of 4 chapters, which are clustering for dataset exploration, visualization with hierarchical clustering and TSNE, decorrelating your data and dimension reduction, and lastly, discovering interpretable features. In this video, we'll learn about the most fundamental of dimension reduction techniques, principal component analysis, PCA and QUAT. PCA is often used before supervised learning to improve model performance and generalization. It can also be useful for unsupervised learning. Let's begin with visualizing the PCA transformation. In the next 2 chapters you'll learn techniques for dimension reduction. Dimension reduction finds patterns in data, and uses these patterns to re-express it in a compressed form. This makes subsequent computation with the data much more efficient, and this can be a big deal in a world of big datasets. However, the most important function of dimension reduction is to reduce a dataset to its bare bones, discarding noisy features that cause big problems for supervised learning tasks like regression and classification. In many real-world applications, it's dimension reduction that makes prediction possible. In this chapter, you'll learn about the most fundamental of dimension reduction techniques. It's called principal component analysis, or PCA for short. PCA performs dimension reduction in 2 steps, and the first one, called decorrelation, doesn't change the dimension of the data at all. It's this first step that we'll focus on in this video. In this first step, PCA rotates the samples so that they are aligned with the coordinate axes. In fact, it does more than this. PCA also shifts the samples so that they have mean 0. These scatter plots show the effect of PCA applied to 2 features of the wine dataset. Notice that no information is lost. This is true no matter how many features your dataset has. Scikit-learn has an implementation of PCA, and it has fit and transform methods just like standard scalar. The fit method learns how to shift and how to rotate the samples, but doesn't actually change them. The transform method, on the other hand, applies the transformation that fit learned. In particular, the transform method can be applied to new, unseen samples. Let's see PCA in action on some features of the wine dataset. Firstly, import PCA. Now create a PCA object, and fit it to the samples. Then use the fit PCA object to transform the samples. This returns a new array of transformed samples. This new array has the same number of rows and columns as the original sample array. In particular, there is 1 row for each transformed sample. The columns of the new array correspond to PCA features, just as the original features corresponded to columns of the original array. It is often the case that the features of a dataset are correlated. This is the case with many of the features of the wine dataset, for instance. However, PCA, due to the rotation it performs, decorrelates the data, in the sense that the columns of the transformed array are not linearly correlated. Linear correlation can be measured with the Pearson correlation. It takes values between -1 and 1, where larger values indicate a stronger correlation, and 0 indicates no linear correlation. Here are some examples of features with varying degrees of correlation. Finally, PCA is called principal component analysis because it learns the principal components of the data. These are the directions in which the samples vary the most, depicted here in red. It is the principal components that PCA aligns with the coordinate axes. After a PCA model has been fit, the principal components are available as the components attribute. This is NumPy array with 1 row for each principal component. Let's proceed with the intrinsic dimension. Consider this dataset with 2 features, latitude and longitude. These 2 features might track the flight of an airplane, for example. This dataset is 2-dimensional, yet it turns out that it can be closely approximated using only 1 feature, the displacement along the flight path. This dataset is intrinsically 1-dimensional. The intrinsic dimension of a dataset is the number of features required to approximate it. The intrinsic dimension informs dimension reduction, because it tells us how much a dataset can be compressed. In this video, you'll gain a solid understanding of the intrinsic dimension, and be able to use PCA to identify it in real-world datasets that have thousands of features. To better illustrate the intrinsic dimension, let's consider an example dataset containing only some of the samples from the iris dataset. Specifically, let's take 3 measurements from the iris versicolor samples: sepal length, sepal width, and petal width. So each sample is represented as a point in 3-dimensional space. However, if we make a 3D scatter plot of the samples, we see that they all lie very close to a flat, 2-dimensional sheet. This means that the data can be approximated by using only 2 coordinates, without losing much information. So this dataset has intrinsic dimension 2. But scatter plots are only possible if there are 3 features or less. So how can the intrinsic dimension be identified, even if there are many features? This is where PCA is really helpful. The intrinsic dimension can be identified by counting the PCA features that have high variance. To see how, let's see what happens when PCA is applied to the dataset of versicolor samples. PCA rotates and shifts the samples to align them with the coordinate axes. This expresses the samples using 3 PCA features. The PCA features are in a special order. Here is a bar graph showing the variance of each of the PCA features. As you can see, each PCA feature has less variance than the last, and in this case the last PCA feature has very low variance. This agrees with the scatter plot of the PCA features, where the samples don't vary much in the vertical direction. In the other 2 directions, however, the variance is apparent. The intrinsic dimension is the number of PCA features that have significant variance. In our example, only the first 2 PCA features have significant variance. So this dataset has intrinsic dimension 2, which agrees with what we observed when inspecting the scatter plot. Let's see how to plot the variances of the PCA features in practice. Firstly, make the necessary imports. Then create a PCA model, and fit it to the samples. Now create a range enumerating the PCA features. And make a bar plot of the variances. The variances are available as the explained _variance attribute of the PCA model. The intrinsic dimension is a useful idea that helps to guide dimension reduction. However, it is not always unambiguous. Here is a graph of the variances of the PCA features for the wine dataset. We could argue for an intrinsic dimension of 2, of 3, or even more, depending upon the threshold you chose. Let's move on to dimension reduction with PCA now. Dimension reduction represents the same data using less features and is vital for building machine learning pipelines using real-world data. Finally, in this video, you'll learn how to perform dimension reduction using PCA. We've seen already that the PCA features are in decreasing order of variance. PCA performs dimension reduction by discarding the PCA features with lower variance, which it assumes to be noise, and retaining the higher variance PCA features, which it assumes to be informative. To use PCA for dimension reduction, you need to specify how many PCA features to keep. For example, specifying n_components equals 2 when creating a PCA model tells it to keep only the first 2 PCA features. A good choice is the intrinsic dimension of the dataset, if you know it. Let's consider an example right away. The iris dataset has 4 features representing the 4 measurements. Here, the measurements are in a NumPy array called samples. Let's use PCA to reduce the dimension of the iris dataset to only 2. Begin by importing PCA as usual. Create a PCA model specifying n_components equals 2, and then fit the model and transform the samples as usual. Printing the shape of the transformed samples, we see that there are only 2 features, as expected. Here is a scatterplot of the 2 PCA features, where the colors represent the 3 species of iris. Remarkably, despite having reduced the dimension from 4 to 2, the species can still be distinguished. Remember that PCA didn't even know that there were distinct species. PCA simply took the 2 PCA features with highest variance. As we can see, these 2 features are very informative. PCA discards the low variance features, and assumes that the higher variance features are informative. Like all assumptions, there are cases where this doesn't hold. As we saw with the iris dataset, however, it often does in practice. In some cases, an alternative implementation of PCA needs to be used. Word frequency arrays are a great example. In a word frequency array, each row corresponds to a document, and each column corresponds to a word from a fixed vocabulary. The entries of the word frequency array measure how often each word appears in each document. Only some of the words from the vocabulary appear in any one document, so most entries of the word frequency array are 0. Arrays like this are said to be sparse, and are often represented using a special type of array called a CSR_matrix and quat. CSR_matrices save space by remembering only the non-zero entries of the array. Scikit learns PCA doesn't support CSR_ matrices, and you'll need to use truncated SVD instead. Truncated SVD performs the same transformation as PCA, but accepts CSR matrices as input. Other than that, you interact with truncated SVD and PCA in exactly the same way. Thanks for watching. In the next video of the playlist, you'll learn about a dimension reduction technique called non-negative matrix factorization, NMF, that expresses samples as combinations of interpretable parts. Also, if you have any questions you can ask them in the comments section and we'll be pleased to answer those. Like and subscribe to stay updated about our upcoming videos about artificial intelligence. See you in the next video.